Hey everybody, welcome to today's lesson. Today's lesson is kind of exciting because I don't know if you're like me, but I'm one of those people that just loves to read the back of any sort of packaging. I love to read shampoo bottles, or I love to read cereal, or any sort of thing that lists all of the ingredients because I always think it's interesting to see those names. And today we're going to be talking about how to name ionic compounds. So hopefully by the end of today's lesson, you'll be able to look at some of those names and have a better understanding of what some of those substances are. I thought since we hadn't really touched base with any Regents-based content just yet, that we could take a look at some examples of Regents-based problems just based on basic ionic compounds. So let's go ahead and take a look. If you're following along by using my guided notes sheets, this will be just right on the sheet for you. If you're not, just pay close attention and make note if any of these are challenging to you at all. So for question number 1, it states, which element reacts with oxygen to form ionic bonds? So we are looking at ionic bonds, and we need to note that an ionic bond, again, is formed between a metal and a nonmetal. Okay, and so we're looking here at which element reacts with oxygen. Oxygen is our nonmetal. And so going from there, we want to take a look and say which of these substances then is a metal. Okay, so we're looking these up. We have chlorine, which is Cl, calcium, which is Ca, hydrogen, H, and nitrogen, N. Remember that you can look at which are considered metals versus nonmetals by just following that staircase on your reference table. Okay, so chlorine falls to the right of the staircase, calcium falls to the left of the staircase, hydrogen falls to the left of the staircase, and nitrogen falls to the right of the staircase. Remember, everything that falls to the left is a metal, and everything that falls to the right is a nonmetal. Now, we're left with two answers here, calcium and hydrogen, and only one of them can be a metal. But don't fall prey to this trick. Remember we said, even though hydrogen is in group 1, it's actually classified as a nonmetal. So therefore, our metal is calcium. Question number 2 asks, the bonds in BaO are best described as. So we're looking here at the bonds between Ba and O. Note that Ba is a metal and O is a nonmetal. Okay, and we are trying to classify these. Now, again, as mentioned previously, an ionic bond is formed between a metal and a nonmetal. So our bond type is going to be ionic. And now looking at the remainder of the question, it says because electrons are transferred or electrons are shared. And literally by definition, this is a definition question, electrons are transferred in an ionic bond. Okay, question number 3 asks us, element X is in group 2 and element Y is in group 17. What happens when a compound is formed between these two atoms? Well, it's important to note that group 2, remember those are classified as your alkali metals, and element Y in group 17, those are your halogens, which are considered nonmetals. Okay, and it's also important to note that metals lose electrons and nonmetals gain electrons. So looking at our answer choices, we are looking at whether or not they gain or lose and what type of bond they form. Now, just the fact that it's a metal and a nonmetal is going to make it really easy to right off the bat say it's supposed to form an ionic bond. Okay, but now element X is a metal and therefore it has to lose, so the only answer is letter D. For question number 4, it asks which Lewis electron dot diagram represents calcium oxide. Now again, we're going to talk about the naming portion today, but you can see that it's the bond between Ca and O, and we know Ca is a metal. We know O is a nonmetal. Okay, and we know that we need to include lots of different components to this. first of all, those Lewis structures, as we've been talking about, need to include charges. So the fact that A and B have no charge is an indication that those are not going to be our answer choices. Looking at C and D, we have our electrons on the metal or we have our electrons on the nonmetal. Well, remember, the transfer of electrons is from metal to nonmetal, which means that our nonmetal should result in all of the electrons at the end. All right, excellent. Let's go ahead and jump into today's lesson, which is going to be naming ionic compounds. And so what I would like to do is I'd like to go ahead and actually start this conversation by taking a look at just some examples of compounds. Now note that today we're going to be primarily focusing, or at least for the first part of our conversation, on what's called a binary compound. So a binary, if you look at the base of the word, okay, bi, that means two. So a binary compound is going to be a compound containing only two elements. So for the first part of today, we're going to just go ahead and focus our energy on the binary compounds, okay? So let's go ahead and get some examples of some binary compounds, and we'll take a look at them to get started. All right, so let's take a look at a chemical formula, RB2O. Okay, so this is our first chemical formula. Now, in order to name this, we need to name our metal ion and our non-metal ion. Okay, so our metal, if you don't know the names of them, this is where that reference table S is going to come in particular handy because you can look them all up. Okay, but our B is going to be rubidium, and O is going to be oxygen. However, this is not how we name this compound. The name of this compound is actually going to be rubidium oxide. And I'm going to go ahead and just name a few, and we'll see if you can figure out the trend of how you name these. Okay, so our first name is rubidium oxide. Let's take a look at another one. Let's look at Na3 P as our formula, and let's go ahead and name that. Okay, so again, we want to name our metal, which is sodium, and we want to name our non-metal, in this case phosphorus, but on our paper it becomes phosphide. Okay, let's name another one. So taking a look at I'm just looking at my side sheet of options of things that I want to name here. Let's do this one, CaBr2. Okay, so again, name our metal, we have calcium. And for Br, this becomes bromide. Let's do one more. Okay, our last example that I want to do for now is going to be Al-I3. Okay, Al-I3. And this is going to give us the name of aluminum iodide. Okay, so just looking at these formulas to name, can we come up with a general rule of how we're going to name binary ionic compounds? And if you take a look, notice that it's always the name of the metal. So our general rule, okay, is going to be, we're going to name our metal, okay, and we're going to name our non-metal. However, with that non-metal, what do we have to do to the ending? We change it from INE, or O-U-S, phosphorus, to I-D-E. Okay, so we're going to name the non-metal, but we're going to change the ending to I-D-E. Now, there are only so many non-metals really that we name here, and I gave you a majority of them already, but just so that we're really comfortable using the lingo here of these non-metal names, let me just go ahead and give you the rest of these. So the only ones that we really haven't used yet are Br, which becomes bromide. Oh, I did use that one. That's okay. It doesn't hurt to list it again. Let's see. We didn't do S, which is sulfide. Okay, let's see, sulfide, bromide, iodide, Cl, right, which is chloride, and two more, F, which is fluoride. Like you may or may not have heard that toothpaste contains fluoride. And lastly, let's just bounce around to this color, I guess. We have, what am I thinking of? I just lost it. Oh, N for nitride. Okay, so those are really the only binary endings that you're going to have. Oxide, phosphide, bromide, iodide, sulfide, chloride, fluoride, and nitride. So really only 8 of them. Okay, now you should also be comfortable with going from name to formula, which again is where that crisscross rule is really going to come into play. So for example, if I gave you the name cesium sulfide, you should be able to look at this and say, okay, let me get the chemical formula. Cesium is Cs, which is a +1. Sulfur is S, which forms a -2. And if we criss and we cross, our formula becomes CS2S. Okay, let's do just one more of those. Okay, let's say I have beryllium oxide. Okay, so we need to look up our information. We have Be, which forms a +2, O, which forms a -2. We criss, we cross, and we get Be2O2, which again can be canceled out, and we can make it BeO. Okay, and that's our final answers there for going from name to formula. Okay, awesome job. What about things that do not only have, or that don't have, if I could speak, that have more than 2 atoms? Okay, so non-binary compounds. Let's go ahead and chat about those. So how do we name non-binary compounds, or compounds that contain more than 2 atoms or 2 types of atoms? Okay, and this is a lot of different types of compounds. So let's go ahead and I'm going to show you a couple of these and then how we name them, and then we'll talk about how we get there. So I'm going to actually be using my reference table for this one, and I'll introduce you to the new table in just a moment. But let's go ahead and get started. So let's make our first compound LiNO3. Okay, so notice we now have more than 2 types of atoms, Li, N, and O. And the question then becomes, how do we name this? So the name of this substance is lithium nitrate. Do you notice automatically how this is different than our previous names? Notice that the end of this ends in ATE. It no longer ends in that IDE ending. Okay, now let's try another one. Okay, let's name this compound. Let's name CaCO3. Again, notice 3 different types of atoms: calcium, carbon, and oxygen. Okay, and this name is actually calcium carbonate. Again, notice that ATE ending, carbonate, okay, indicating that it's not just a binary substance. Okay, let's see. Really quickly, let's do just 2 more. All right, what about this one? NH4Cl. Okay, we contain NH and Cl. This name is ammonium chloride. Now, you might be thinking, well, Miss Daly, this one does end in IDE. Why is that the case? And the answer is it depends on where your multi-atom ion comes from. And we're going to introduce that term in just one moment, but I'll come back to that one and we'll talk about that a little bit further. Let's just do one more. All right, so last one that we're going to talk about, let's do SR, okay, 3PO4 2. Now, notice that this one does look different too. It has these parentheses in there. We're going to talk about what that means in just one second also. So the name of this one would be strontium phosphate. Okay, so these binary compounds actually contain what is called a polyatomic ion. Okay, and so I'm going to scroll down and note that here. So the non-binary contain a polyatomic ion. And notice that word poly. Now, in history class, you may have heard this term polytheism or polytheistic, which means you typically believe in many different gods. And so poly means many. And so when we're talking about polyatomic ion, we are talking about an ion made from more than one atom. Okay, and so let's go back up and I want to just show you where those polyatomic ions are in your compounds that we looked at. So you can kind of tell from the name where the poly ion is. So lithium is named totally normally, which means that your poly ion is actually this ion, nitrate. Calcium, again, named normally, so our carbonate is this ion here. Ammonium chloride, which of these is named normal? Well, you might not know this just yet, but ammonium is not an element, okay? But you can see from the name that the chloride is named normally, which means that ammonium is our poly ion. And in the case of strontium phosphate, PO4 is our poly ion. Okay, now here's what's amazing about these polyions and what makes your life just a little bit easier is you don't need to memorize these at all. All of these polyatomic ions are actually found on reference table E. Okay, and it is truly awesome because they are literally all right here for you. They give you the names, they give you the charges, and it makes your life a lot easier. So let's talk about now, we have these formulas, we go to name, okay? Let's talk a little bit about going from name to formula. And I do want to point out too, for just 1 second, to be really careful about naming polyions, only because if you look really closely at reference table E, there are a lot of them that are very close in name. For example, at the bottom of the left-hand column on reference table E, we have hypochlorite, chlorite, chlorate, and perchlorate. Okay, as well as to the right-hand side, nitrite versus nitrate. So be very careful and make sure you double check which one we are using. Now let's talk about going from name to formula, because I want to just talk a little bit more about that crisscross rule and some specifics that we need to be really careful with here, okay? So let me give a couple of names and we'll practice using the crisscross rule that we used for coming up with formulas before. So let's start with sodium, okay, sulfate, sodium sulfate, okay? So how do we go from name to formula? Again, we're going to use crisscross. So we need to look up the charges of these ions. Now, sodium, the sodium ion is Na+1. And sulfate, again, that ATE ending that you see should be indication to automatically flip to reference table E. So I flip to reference table E. I'm careful to make sure I'm using the correct ion, and I see that the sulfate ion is SO4 minus 2, or as it's written there, 2 minus potato. Now, here's the rule that you must absolutely follow, okay? And I'm going to star it right above it. When crisscrossing, okay, with polyions, okay, make sure to use parentheses. I probably spelled that wrong. There's a reason I didn't become an English teacher. Okay, so what do I mean by that? I mean, you are going to take that polyatomic ion and you're going to put that in parentheses. And the reason we have to do that is because this ion, SO4, that's bonded together. And we can't take that 4 away. And a lot of times students forget that and they start trying to crisscross using that 4. But that 4 is literally bonded. Those 4 O's are bonded to that S and we can't touch that. Okay? So let's go ahead and crisscross. We are going to criss all the way outside the parentheses and cross all the way down, and we end up with Na, and remember we're using this, right, Na2 parentheses SO4 1. Now again, that 1 is redundant, we don't need it there, and if there is a 1 there, then you can actually drop the parentheses, Na2 SO4. So if there is only 1 poly ion after crossing, okay, you can drop those parentheses, okay? Otherwise, you have to keep them. So let's try another one where we do have to keep them, okay? Let's do aluminum. Aluminum carbonate. Okay, so we have Al plus 3. Now we go to reference table E for our carbonate, which is I'm blanking, CO3. I don't know why that was so hard, minus 2. Okay, and now we are going to put our carbonate in parentheses. CO3 goes in parentheses. We criss and we cross, and we end up with Al2 parentheses CO3 3. Okay, and we have to have that there because now this tells us that we have 3 of these carbonate ions. All right, everybody, I think this video is long enough. We will do some practice with all of this in class, and I look forward to seeing you on Monday. Have a great weekend.